Einstein might be wrong. All hell broke loose in the physics community.
Einstein's ideas might have been wrong. Let that idea settle for a moment. One of the greatest intellectuals in human history, the man whose theories of relativity reshaped our understanding of physics, is now at the heart of a major scientific controversy. A recent groundbreaking study published in the past few months has rocked the scientific community. It challenges the fundamental principles of modern physics and raises questions about some of the most treasured beliefs regarding the universe. If Einstein's ideas were flawed, what does that mean for how we perceive reality? And where do we go from here? To fully grasp the gravity of this study, we must first look at Einstein's lasting impact, especially his general theory of relativity, which he introduced in 1915. This theory transformed our conception of gravity, space, and time, replacing Newton's classical view of gravity as a force with the revolutionary concept of gravity as the curvature of space-time. Einstein's equations elegantly describe how massive objects like stars and planets bend space-time, creating what we perceive as gravitational pull. Over the years, this theory has been confirmed repeatedly, from the bending of light during solar eclipses to the detection of gravitational waves in more recent times. However, despite its robust success, general relativity has always had its limitations. For example, it has never been able to reconcile with quantum mechanics, the theory that governs the behavior of particles at the smallest scales. While general relativity excels at describing large cosmic structures like galaxies, black holes, and the expansion of space itself, quantum mechanics deals with a completely different domain where uncertainty, probability, and wave-particle duality are key factors. For decades, scientists have sought a unified theory of quantum gravity that could explain both the macroscopic and microscopic realms. But now, it appears that the flaws in Einstein's theory are becoming too significant to overlook. The recent study, carried out by an international team of astrophysicists and published in a leading scientific journal, reveals that the universe is behaving in ways that general relativity fails to predict. Using data from advanced telescopes and satellites, researchers have noticed discrepancies in how galaxies rotate, how dark matter is distributed, and how the universe is expanding. These anomalies suggest that our current understanding of gravity might be incomplete or even deeply flawed. One of the most surprising discoveries centers on dark energy, an elusive force driving the accelerated expansion of the universe. First detected in the late 1990s, dark energy is a mysterious phenomenon that contradicts Einstein's predictions. General relativity suggests that gravity should slow down the expansion of the universe over time. However, observations of distant supernovae and the cosmic microwave background have shown that the universe is expanding at an increasingly faster rate. To explain this, scientists introduced the concept of dark energy, which they believe accounts for about 68% of the universe's total energy content. Yet, dark energy remains one of the most perplexing aspects of modern physics. It's invisible, doesn't interact with matter or light, and can only be inferred from its effects on the cosmos. Einstein's theory accommodates dark energy through the introduction of a cosmological constant, a term he initially proposed and later discarded in an attempt to model a static universe. But the new study suggests that this explanation is inadequate, as the latest observations of dark energy do not align with the predictions of the cosmological constant. Instead, they point to a much more complex and dynamic phenomenon that might necessitate a new theory of gravity to fully comprehend. Additionally, there's the enigma of dark matter. Like dark energy, dark matter is invisible and mysterious. It's believed to account for about 27% of the universe's mass, and is thought to provide the gravitational force that holds galaxies together, preventing them from flying apart as they rotate. Without dark matter, the observed motion of stars and gas within galaxies would be inexplicable. Yet, after decades of searching, scientists have yet to detect even a single particle of dark matter directly. The new study adds another layer of mystery. showing that the distribution of dark matter in certain regions of the universe doesn't match the predictions made by general relativity. This raises the possibility that either our understanding of dark matter is flawed or that gravity behaves differently on cosmic scales. Perhaps the most controversial aspect of the study involves the Hubble constant, which is used to measure the rate at which the universe is expanding. For years, scientists have struggled with a cosmic tension. The measurements of the Hubble constant taken from the early universe, such as through the cosmic microwave background, produce a different value from measurements taken in the nearby universe, such as from supernovae and Cepheid variable stars. This growing discrepancy suggests that something fundamental is missing in our cosmological models. The new study argues that this tension cannot be resolved within the framework of general relativity and instead suggests that a new theory of gravity is needed, one that accounts for dark energy, dark matter, and the evolution of the universe in ways that Einstein's equations cannot. This does not mean that general relativity is entirely incorrect. Like Newton's laws before it, Einstein's theory has proven to be extraordinarily accurate in many contexts. But just as Newtonian mechanics was eventually superseded by relativity, it's possible that relativity itself may eventually give way to a more comprehensive theory. What might this new theory look like? Several possibilities are already being explored. One concept is modified gravity, which suggests that the laws of gravity might change under certain conditions or at specific scales. Another is emergent gravity, which posits that gravity is not a fundamental force, but rather a result of deeper quantum interactions. There are also theories involving extra dimensions, alternate forms of energy, or entirely new particles. Each of these ideas represents a significant departure from the current understanding, yet all aim to reconcile the discrepancies in our knowledge of the universe. The potential consequences of these new findings are enormous. If Einstein's theory is incomplete, it means we must reconsider our entire understanding of the cosmos. Questions about the age of the universe, the fate of galaxies, the nature of black holes, and even the origin of time itself are now open to debate. While this uncertainty may be unsettling, it also highlights the power of science, the willingness to challenge long-held beliefs, acknowledge what we don't know, and push the limits of human understanding. This pursuit is far from over. The study is just the beginning of what could be a long and ongoing debate, with new data needing to be verified, alternative theories needing to be developed, and experiments needing to be conducted to test these new ideas. It may take decades or even centuries, but it is a vital step in our quest to understand the universe. As we look to the future, one thing remains certain: Einstein's legacy will continue, even if his theory of general relativity is eventually replaced. His contributions to science have shaped the course of modern physics and inspired generations of scientists to think boldly and creatively about the nature of reality. In this sense, Einstein's influence will remain, even as we embark on new intellectual journeys into the unknown. So, was Einstein wrong? The answer is both yes and no. His theory of general relativity was a groundbreaking achievement, a testament to human ingenuity. But like all scientific theories, it is not the final answer. Science is a process of constant refinement, and the discovery of new evidence should be seen as a triumph, not a failure. It demonstrates that we are still learning, still questioning, and still searching for the truth. And in that quest, we honor the very essence of Einstein's legacy. This new study does not just call into question Einstein's theory of general relativity. It forces us to re-examine some of our most fundamental assumptions about the universe, including time itself. Einstein's equations fundamentally link space and time into a single entity known as spacetime. But what if time as we perceive it isn't real? What if it is simply an illusion, a construct created by the human brain to make sense of an incomprehensible cosmos? Some physicists are already exploring this unsettling idea. In a universe where Einstein's equations no longer hold true, the nature of time could be radically different. The study suggests that dark energy, the force driving the expansion of the universe, might actually be a manifestation of something more fundamental, something that ties space, matter, and time together in ways we don't yet fully understand. This line of thought opens up a host of philosophical and scientific questions. For example, does time flow in one direction as we experience it, or is it as static and eternal as the space we inhabit? In Einstein's universe, time is relative. It speeds up or slows down depending on how fast you're moving or how close you are to a massive object. But the new research hints that time may not exist as a continuous flow at all. Instead, it could be an emergent property that arises from deeper, undiscovered physical laws. If time is an illusion, so too might be causality, the very idea that one event leads to another in a linear progression. This challenges not only physics, but the entire framework of human understanding. How do we make sense of a universe where events do not unfold the way we perceive them? How do we reconcile our lived experience of the past, present, and future with a reality that may not fit into those categories? These aren't just theoretical questions. They have profound implications for technology, consciousness, and humanity's future. Take quantum mechanics, for instance. At its core, quantum mechanics defies our classical understanding of time and causality. In the quantum realm, particles can exist in multiple states simultaneously, and events can influence one another regardless of distance. This is known as quantum entanglement. Some physicists have proposed that time itself might be a byproduct of quantum processes, an emergent feature of the universe that only arises when observed. If this is true, our perception of time might not be a fundamental property of reality, but a quirk of human consciousness. Now, imagine the technological ramifications of this discovery. If time is not a fixed dimension, but something that can be manipulated or bypassed, the possibilities for human innovation are enormous. Quantum computers, which are already on the cutting edge of technology, could take on an entirely new role by harnessing the quantum nature of time. These devices might one day allow us to peer into the past or predict the future with unprecedented accuracy. They could revolutionize fields such as medicine and artificial intelligence, unlocking capabilities we can barely imagine. But this also raises ethical concerns. If we gain the ability to manipulate time, what does that mean for free will, morality, and the very nature of human existence? These are questions we cannot afford to ignore. As history has shown, every scientific breakthrough comes with unintended consequences. The more we learn about the universe, the more responsibility we have in deciding how to use that knowledge. Another profound impact of this new study is its potential to advance the search for a unified theory of everything. For decades, physicists have tried to reconcile general relativity with quantum mechanics, a task that has proven notoriously difficult. String theory, loop quantum gravity, and other frameworks have attempted to bridge the gap, but none have gained universal acceptance. This new research suggests that the problem may not lie in our theories themselves, but in the assumptions that underlie them. If Einstein's equations are incomplete, then the entire foundation of modern physics might need to be reevaluated. One promising direction of research is holography. According to the holographic principle, the entire universe could be a projection of information encoded on a lower dimensional surface. First proposed in the context of black hole physics, this idea has gained traction as a possible framework that could unify gravity and quantum mechanics. If true, it could mean that the three-dimensional world we experience is just a shadow of a deeper, more fundamental reality, one where the laws of general relativity no longer apply. The consequences of holography go far beyond physics. If the universe is a hologram, then reality itself may be an illusion. This raises profound questions about consciousness and humanity's role in the cosmos. Are we merely passive observers of a preordained cosmic drama, or do we actively shape the reality we inhabit? Some physicists and philosophers argue that consciousness could be the missing piece of the puzzle, a fundamental aspect of the universe as essential as matter, energy, and space-time. If that's the case, then understanding the true nature of the cosmos may require us to look inward as well as outward. Finally, let's consider the implications for the multiverse. If Einstein's theory is incomplete, it suggests that our universe might not be the only one. Instead, it could be part of a larger multiverse, where different regions of space-time operate under different physical laws. Once thought to be science fiction, the multiverse hypothesis is gaining serious scientific support. The discovery of dark energy and the anomalies in the Hubble constant suggest that our universe might not be isolated but part of a broader, dynamic framework. The multiverse hypothesis raises many questions. How did these universes come into existence? Do they interact with one another? What does this mean for our understanding of reality itself? If there are infinite universes, each with its own unique set of physical laws, the concept of truth becomes relative. What is true in one universe may not hold in another, challenging not only physics, but also philosophy. It forces us to confront the limits of human knowledge. As we wrestle with these questions, it's important to remember that science has always been a journey of exploration and discovery. Every time we think we've reached the edge of understanding, new evidence emerges to challenge our assumptions. Einstein understood this better than anyone. He famously said, "The important thing is not to stop questioning. Curiosity has its own reason for existing." Those words remain as relevant today as they were a century ago. The new study challenging Einstein's theory of relativity is not the end of the story. It's the beginning of a new chapter in the history of science. It reminds us that the universe is far more complex and mysterious than we can imagine, and that our journey of discovery is far from over. As we continue to push the limits of knowledge, we must remain open to new ideas, question even our most cherished beliefs, and embrace the unknown. What lies ahead is uncertain, but one thing is clear. The universe still has many secrets to reveal. As we stand at the threshold of a new era in physics and cosmology, we can take comfort in knowing that the spirit of inquiry that drove Einstein and his contemporaries continues to inspire us today. The road may be long and filled with challenges, but it's a journey worth taking. A journey into the heart of the cosmos and the very nature of reality. As the new research forces us to reconsider Einstein's general relativity, the questions it raises about the multiverse go beyond mere academic curiosity. If our universe is just one among infinite others, each with its own set of properties and laws, then how does our place in this vast multiverse shape our understanding of existence? This isn't just a question of physics, it's a question of meaning. For many physicists, the multiverse hypothesis is both exhilarating and unsettling. It suggests that everything we know, the galaxies, stars, and planets, might be part of a larger framework operating under principles we have yet to fully grasp. If each universe operates under its own laws, constants like the speed of light or the gravitational constant might vary between them. Some universes might not have stars at all, and in others, life as we know it might not exist. This raises the profound question, why does our universe allow for life to flourish? At the heart of this lies the fine-tuning problem, the remarkable precision with which the laws of physics in our universe seem calibrated to support life. If gravity were just a bit weaker, stars couldn't form, and the universe would remain a cold, dark void. If the electromagnetic force were a little stronger, atoms wouldn't hold together, and matter as we know it couldn't exist. Some scientists speculate that our universe is just one of many, each with its own unique properties. In this multiverse framework, the existence of a life-supporting universe like ours isn't a miraculous coincidence, but an inevitability. This idea leads to even deeper questions. How did the multiverse come into existence? Is there a process that generates these universes? Some theories suggest that the multiverse arises from quantum fluctuations in higher dimensional space, while others propose it could result from eternal inflation, a process where space-time continues to expand. creating new universes in its wake. These ideas are tantalizing, but also present a challenge to empirical science. How can we observe or test the existence of universes beyond our own, when they are by definition beyond our observational reach? Critics argue that the multiverse is speculative and metaphysical rather than scientific. However, proponents contend that the multiverse is a natural extension of existing theories. If quantum mechanics and general relativity hold true, the multiverse isn't just possible, it's likely. While we may not be able to directly observe other universes, some believe their existence could leave subtle traces in our own. For example, if universes collide, these collisions might create anomalies in the cosmic microwave background, the faint afterglow of the Big Bang. By studying these anomalies, scientists hope to gather indirect evidence of the multiverse. The implications of this idea go far beyond physics. If there are infinite universes, it forces us to confront some of the deepest questions about the nature of reality itself.